We all use MySQL and Postgres daily, but very few engineers understand how relational databases are actually designed internally. In this video, we'll break down the system design of a relational database, storage, indexing, transactions, and scaling, without unnecessary theory. You might wonder, if relational databases already exist, why do we need non-relational databases at all? The answer lies in scale and latency. Relational databases prioritize correctness and strong consistency, which makes them difficult to scale horizontally across regions. When systems need massive global read-write throughput with low latency, these guarantees become a bottleneck. That's why platforms like Discord use schemaless, non-relational databases, because flexibility and horizontal scalability matter more than strict relational constraints at that scale. MySQL and PostgreSQL are both relational databases, but they are designed with different priorities. MySQL focuses on speed, simplicity, and read-heavy workloads, which is why it's popular for web applications. PostgreSQL focuses on correctness, advanced SQL features, and strong transactional guarantees, making it ideal for complex systems. The storage engine of MySQL is faster, but Postgre trades internal guarantees. Multi-concurrency control for MySQL is limited, but for Postgre, it's more safe overall feature depth as Postgre add common features have MySQL. So what and when to choose? MySQL runs overall heavy apps that has simple schemas and can handle massive web traffics and faster scaling. And for Postgre, when the software works on financial data, auth systems, and analytics. Let's walk through the high-level architecture of a relational database and understand how a SQL query actually gets executed internally. Everything starts at the client side. An application sends a SQL query over the network using a database protocol. This request first enters the protocol layer, whose only responsibility is communication, handling connections, authentication, and converting network messages into internal commands. Once the query crosses the protocol layer, it enters the relational engine, which is the brain of the database. The first component here is the command parser. The parser validates the SQL syntax and converts the query into an internal representation, often called a query tree. This query tree is then passed to the optimizer. The optimizer's job is not to run the query, but to decide how to run it. It evaluates multiple execution strategies, like which indexes to use, join orders, and access paths, and selects the most cost-effective plan based on statistics. The result of this phase is a query execution plan, which is handed over to the query executor. The executor follows this plan step by step and coordinates with the lower layers to actually fetch or modify data. At this point, control moves into the storage engine. The storage engine is responsible for data correctness and durability. All read and write operations go through access methods, which know how to scan tables, traverse indexes, and locate rows on disk. Any modification is coordinated with the transaction manager, which enforces ACID guarantees. Before data is changed, the operation is recorded in the transaction log, ensuring the system can recover safely after a crash. Actual data pages are not read directly from disk every time. Instead, the buffer manager checks the buffer pool, which is an in-memory cache of frequently accessed pages. Modified pages are marked as dirty and flushed to disk later for efficiency. Finally, results flow back up, from the storage engine to the executor, through the protocol layer, and back to the client. The key takeaway is this: a relational database is a layered system where each layer has a single responsibility: parsing, planning, execution, storage, and durability, working together to guarantee correctness even under concurrency and failures. Now let's zoom into the storage engine and understand how relational databases actually store data on disk. At the lowest level, a relational database does not store individual rows directly on disk. Instead, data is stored in fixed-size units called pages. A page is the smallest unit of I/O between memory and disk, not a row. Each page starts with a page header, which contains metadata such as the page ID, page type, free space information, and internal pointers. This header allows the database engine to understand what kind of data the page holds and how to interpret it. Below the header, we have the actual data rows. Rows are stored sequentially within the page, growing downward as new rows are inserted. Importantly, rows are not addressed by their physical position alone. At the bottom of the page we have row offsets, also called the slot array. These offsets act like an index inside the page, each entry pointing to the exact location of a row. This design allows rows to move within the page during updates or compaction without breaking logical references. The unused space between the last row and the offset array is called free space. Free space is critical for performance because it allows new rows or row expansions without immediately allocating a new page. When a query needs data, the storage engine does not fetch a single row. It loads the entire page into memory through the buffer pool. This is why databases are optimized for page-level access, not row-level access. If a row is modified, the page becomes a dirty page, meaning changes exist only in memory. These dirty pages are later flushed to disk in batches, improving write efficiency and durability. The key takeaway is this: relational databases are page-oriented systems. Pages provide the balance between efficient disk I/O, flexible row management, and strong durability guarantees. Indexes exist to avoid full table scans, but not all data structures work on disk. Databases use B+ trees because they are optimized for disk access, not memory. B+ trees keep data sorted, minimize disk reads, and allow fast-range queries. Most importantly, they have high branching factors, which keeps tree depth small, even for billions of rows. Now, the ACID properties relational databases guarantee correctness using ACID transactions. Atomicity is enforced using write-ahead logging, where changes are logged before data is written. Isolation is handled using locks or MVCC, so concurrent transactions don't corrupt each other. Durability ensures committed data survives crashes by replaying logs during recovery. Relational databases scale vertically first by adding CPU, memory, and faster disks. To scale reads, replicas are added, but writes still go to a single primary. Horizontal scaling through sharding is hard, because joins and transactions break across nodes. This is a deliberate trade-off, correctness over massive scale. I tried to explain major relational database core concepts in detail, and it allows choosing the right database for the organization. Also, make sure to subscribe for more system design concepts. It really helps me. Peace out.